Mm-hmm.
All right, now that I'm recording, we'll start again. Hello, everyone. Hope you're all having a good week, had a nice weekend. Today, we're going to be making a presentation on price smoothing. As I mentioned earlier, this will include Kalman filters. We'll go over a few other simpler techniques that some of you may be familiar with already. So let's hop right in. All right. So one of the biggest things that you're going to be concerned with in your algorithms is, of course, price. But the term price is a little bit broad and can be non-specific. There are several different factors that you can look at when you're talking about price. Maybe you want the open of a stock. You want its close, its high, its low, etc. Maybe the bid, the ask. All of these different statistics will represent the action of a security at one specific point in time. If I said, hey, Guhan, can you let me know what the high was of Tesla today? He would output one number, greatest value it reached. Now, if you just want to look at price, even if you would just say, okay, let's look at only the closed data for each bar, and you just wanted to plot this data, you would notice that the chart that comes up, the stock price chart, would be pretty erratic in its movement. And this can make it difficult to work with and a little bit difficult to interpret. For example, you're going to see some pretty sharp movements. If you look at the intraday chart for, let's say, Apple today, you'll see that there are a lot of jagged edges along the graph and along its movement throughout the day. For this reason, you often don't want to use your raw price data, but rather find some way to smooth it and make it a little bit more, I guess, clean, so that when you pass it into an algorithm, it can have a better, it'll have a better success rate, since whatever operations you're performing will be applied to a less erratic and less jagged set of data. For this reason, we recommend that you use some kind of smoothing algorithm. This will help counter a lot of the pitfalls of price, because instead of just looking at the exact price point right now and putting that on your plot, the smoothing algorithm will instead look at your price in relation to a few others, apply some sort of weighting or some sort of transformation, and then output a data that doesn't just reflect the immediate movement, but also takes into account the transition that took place to get to your current price value. So the first technique that we're going to talk about for smoothing is moving averages. So what does a moving average do? Well, it's actually rather simple. It will take in a list, array, whatever you want to call it, of prices, and apply a certain algorithm, which we'll show you a few examples in the coming slides, to smooth out the price. And instead of just reflecting every single whip shot, every single quick movement, it'll get you a bit more of a display of the actual process underlying the stock's movement. What do I mean by this? Well, whenever you're looking at a stock price, there's going to be a lot of factors that influence it. One of them is going to be noise. This applies to any process that you observe in life. Oftentimes, you can kind of split up any process you observe, be it a time series, price data, some sort of chart you collect in an experiment involving nature or whatnot. You can oftentimes decompose this into a trend and some sort of noise factor. In applying a moving average effectively gives you an idea at what is this actual trend, so that you don't get caught up in all the noise. So the first example of a moving average that we're going to show you is called a simple moving average. This algorithm is quite simply a way to calculate the arithmetic mean of the last n inputs and output whatever value is currently the mean value. So let's look at a stock. We're going to call it SQC. So the last 10 days, I have listed what the open prices are for SQC. If you were to just look at a plot of SQC's current price data, well, you would simply get these 10 numbers on your screen, and there would be lines connecting them over whatever interval. Well, what if we were to instead plot a 5-day moving average? In this scenario, there would be no data for the first 4 days, but as we can see, the numbers that are outputted for the next, 6 days are a little bit more, how do I say it, smoothed out. they're less witty and erratic. You see SQC goes from 10 to 1010, 1001, 988, so on and so forth. Whereas here it stays a little bit more in line and it doesn't suffer from the same day-to-day just wild variability and randomness that you would observe if you were to just straight up plot the data of SQC's price. So I actually went ahead, did a little bit of coding, and decided to show you guys what this would look like graphically. So if you were to plot the raw data, this is roughly what I showed you before, the same stock prices. That is your orange line. As you can see, that has that erratic noise impacted kind of design where it's a little bit hard to get a handle of. Whereas the 5-day SMA is a lot smoother. You can really grasp the underlying trend a lot better by looking at the 5-day SMA because it's a lot more intuitive to interpret. There's a lot less of that erraticism, that randomness. All right, the second algorithm that we're going to go over is a bit more advantageous than the simple moving average, in my opinion. It's called the exponential moving average. Now, with your SMA, you have two kind of, I guess, possible issues that you could run into. The first is that each of the past 5 days have the same weight. So we assume, they kind of have the same importance. But a lot of time in your models, you might want to look a bit more and give preference to the data that's most recent. So the current price of the stock, the price of the stock yesterday, the day before yesterday, et cetera, et cetera. Another problem is that once you exit that 5th day, once you go on to the 6th day, whatever price frame, whatever price point was last previously, so whatever was the 5th day's data is simply dropped. You basically say, okay, I no longer care about that point, disregard it, doesn't impact us for the rest of the way, which also could be quite dangerous because if you have a very short time frame, like 10 days, removing one data point, if it was a very large move upward or downward, could really impact how you're actually looking at the movement of your prices over time. So I decided to use those same data points and show you what this exponential moving average looks like as opposed to the raw data. So if we go back 2 slides to the simple moving average, we saw that it still would have a little bit of erraticism, and we can definitely see a bit more divergence between the moving average and the actual data. With the exponential moving average, we get even smoother, even more of a look at just the underlying trend without accounting for any other noise that's applied from wild, erratic trading behavior that we would all witness throughout a trading day. The exponential moving average, the way it's calculated is you would specify a certain quote unquote window for your data. And based off of this window, it would weight the most recent day's exponential moving, the most recent day's price and the previous day's EMA accordingly in a method that is proportional to the two. I can give you the math later. All right. Now, we take these kind of basic ideas from a simple moving average and exponential moving average, and we go move on to the Kalman filters, which are kind of the next level. So the Kalman filter is very useful in a lot of studies involving physics, or if you're looking at a natural process or anything that you can't get a 100% accurate estimate of. This next example will be a bit of an extreme reality that illustrates the needs for this. So some of you may have saw this in the news over the summer, but there is currently an asteroid that is hurling towards the Earth. Full disclaimer, it won't hit us for like many lifetimes, so we're fine. But we don't know exactly if or when it will hit the Earth, but it's pretty important to know if we're going to die one day. Right now, it's pretty far away, so we can put telescopes at it, use radar, whatever technology we have. But at the end of the day, I mean, we won't be able to get a 100% accurate estimation of where it is right now, where it was yesterday, how fast it's moving, so on and so forth. But I mean, scientists, they have a lot of equations and models to just perfectly represent this path, so we're good. Or we aren't good. The reality is, whenever you're just looking at an asteroid through space or any other kind of physical process, you don't really know exactly how, you can't really get a 100% accurate measurement of what you're looking at. In this example, the asteroid is light years away from us, and no matter how strong our telescopes and our radar are, we're not going to be able to 100% say this is the exact position of the asteroid. One big influence we're going to encounter is noise experienced by, let's say, the radar that we shoot out throughout space. It's going to move around a bit, get influenced. Eventually, when it hits that asteroid, we don't really know a few factors, like for one, how much the asteroid has moved since we hit it, what happened to the rays we shot out in the process, etc. So given all of this, what can we really do to say, all right, we know that our data isn't 100% perfect. We're uncertain about certain aspects, and we don't really know the true physical state of the asteroid. Well, for that reason, we will apply smoothing algorithms. In this example right here, we're going to talk about the Kalman filter. Now, a very high-level overview of what is a Kalman filter is that a Kalman filter will take in data, and based off of whatever data was passed in, current states, last states that you recorded, etc., it's going to generate a prediction of where the element is now. Usually, when you're talking about predictions, you're trying to say, okay, where is this car going to move in the next few minutes? Where is this stop going to move tomorrow? Where am I going to, I don't know, sit down in 3 minutes? You're always talking about the future. What's interesting with a Kalman filter is you're more interested in the present sometimes, because you can't know with 100% certainty where a stock could be. This for the chat. So that's very accurate. That's I'll go into that later, Kaden. But so where was I? Yeah. So you're actually trying to figure out where are we now. This goes back into the idea I mentioned before about how a stock or any other time series can be decomposed into a trend of noise. This noise is going to be somewhat of a constant factor. So whenever you're trying to make a model in your trading algorithms, you're really going to want to focus on this trend aspect. You kind of want to discount the noise. So if you use a Kalman filter, you can get a better idea of, well, this trend aspect we mentioned before. And my keyboard stopped working. Okay, there we are. All right, so now I'm going to get into the, I guess, more technical aspects of the Kalman filter really briefly. The technical term for, I guess, what family of algorithms a Kalman filter falls in is state space model. This is a very fancy way to say a mathematical model of a physical system that keeps track of the state of the current system given a number of inputs. So what does that mean? If I am watching a cat chase a mouse around my house, I'll take a look. I have a radar machine. I'm going to point at the mouse. And I'm going to try to look at the mouse at all times. This radar will track the position of the mouse. Maybe also say, all right, calculate the velocity of the mouse, whatever it is I'm interested in. And then whatever data I get from my radar gun, I'm going to pass into a Kalman filter. When I give it a certain number of inputs, the Kalman filter is going to go behind the scenes under the hood and use some linear algebra, a little bit of probability theory, more advanced math than I'll be going over today. And it's going to spit out a projection that says, hey, based off of all the information you gave me, based off everything you told me, this is where I think the mouse is. So if you were interested in tracking, okay, where is the mouse right now, where is it going, etc., you could theoretically just say, all right, here are all the positions that we listed. So this is where the mouse is. But same with the asteroid data. No matter how strong of a radar gun you use, if the mouse is very far away, for example, you can't know with 100% accuracy where this mouse really is. So you have to understand that there is some noise that's factored in, and that will, I guess, solely your measurements. The Kalman filter is simply a really nice algorithm that's been studied, that's been developed, etc., which we can use to figure out where is this mouse. Second. All right, so what do we do exactly with the Kalman filter? Well, as I said before, you're going to pass in a certain number of inputs. From these inputs, the Kalman filter is going to do a bunch of fancy linear algebra, probability, etc. Really nothing to worry about. And from there, it's going to calculate a few metrics, we'll call it. So one metric is the Kalman gain, which, as the name kind of implies, is simply how much does this filter think that you went up. The other three metrics are sensor confidence and mathematical confidence. This second term of the equation, the sensor confidence over sensor minus math confidence, is kind of like I shouldn't call it a weighting or a smoothing factor to account for the fact that the data you passed in isn't going to be 100% precise. It's not going to be the exact position of of the object undergoing your process. So this is essentially a really nice mathematical way to account for the fact that you have some unpredictable, unconfident, some unpredictable factors impacting your calculations, making them unconfident. Now, the last slide of tonight's presentation, I'm going to show you guys basically a real world example of applying a Kalman filter. In this scenario, maybe it was like a spring or something that they were measuring over time as it was bouncing back and forth. So as we see in blue, you have the actual measurements of the position of this object that I'll assume is a spring. And in red, we see the Kalman filter. As you can see here, it takes this extreme erraticism, this wild back and forth, almost bungee jumping behavior, and it outputs a single, very easy to understand line that definitely coincides with the slope of these these measurements, and definitely gives you an idea into the underlying process. So if you were to plot a Kalman filter, the easy way to interpret the output is simply look at the line and look at its slope the same way you would with any kind of equation or graph or whatnot. If you want to use it mathematically, you can basically do the same thing, but instead of looking at it with your own eyes, you're just going to pass numbers into a system. So the number one most important function of Kalman filters is that they will give you a cleaner look into a stock's trend in their price, their volume, etc., while discounting for the noise that impacts your readings. When you just look at the trend, you can make a lot better predictions. That's it from me. Guhan, you want to add anything?
No, John, I think you covered everything for today.
Awesome.
We do have Connor here. Connor, do you want to add anything or give some input?
I don't really think anything I could add would be of too great help. What I would say is an interesting route to go down, especially when it comes to state space modeling, is looking at how some internal states can affect or even calculate other internal states. For example, I remember something that we did in our algorithm was that we were able to calculate beta of our algorithm from a Kalman filter of how our algorithm was working. I obviously don't have a presentation of that off the top of my head, but I think that's a very interesting route to go down.
Wow, that's actually pretty cool. Thanks, Connor. So we'll open up to questions now if anyone has any questions. Could you link any helpful videos or sites on the resources channel about implementing this in Quant Connect?
Yes, sort of. So we can definitely give you which package you can use in Quant Connect to do this, and some sort of video or some sort of image to show you it actually being implemented, so you can kind of get an understanding of how you can do it.
Connor sent a link in the chat, everyone, and we'll also repost this on the Discord. Do we have any other questions? Any more concerns? All right, I think if that's it, John, we can stop the recording now. This should be up pretty soon.